Right. So the assignment that is due tonight is 3.6, and 3.6 is more position, velocity, and acceleration. And acceleration. I don't know if I squished that in too much or not. Okay, so let's look at a graph really quickly that will say that this is time. And so the x-axis is time and the y-axis is our distance. So if I used, if my function was, I don't know, 2x plus 3, something like that, or if we wanted to do something with more of a curve, that maybe we could throw in a square in there. So at least maybe the first half would be something squared. It would actually be something, this would be something like this. And if this graph represented position, then whatever value I plugged in for x, that would be my time, it would tell me my position at that particular time. That's why we would call this a position function. Now let's consider what it means to be a slope. If I found the slope right here of that particular position, so that instantaneous slope at that point, what units would make up the slope? My rise would be what? Yeah, my rise. So if you recall, slope is defined by rise over run. My rise is distance. My run is time. What kind of units are we talking about when we talk about distance over time? That is velocity. Distance over time would be miles, that's distance, per hour, that would be dividing by a time, or meters per second would be another type of velocity. So when we take, if we have a position function and we find the slope at any given point, then it's going to give us the velocity at that given point. Do we have a handy way of creating, if we're given a position function, do we have a handy way of finding the velocity function? Do we have a method? Josh, what do you think? Do we have a method that would allow us to transform a position function into a velocity function? Yep. Yeah, we could just use the derivative. In fact, that's really what the derivative does. The derivative finds the instantaneous rate of change. So if we take the derivative of a distance versus time function, we get a velocity function. Now what happens, let's consider another graph where we have, I hate when it does that, where we have, this is time, and this is my velocity. Now recall that time is measured, we could say in seconds, and velocity, let's say that this is measured in meters per second. So we have some curve like this, and I want to find the instantaneous rate of change. So here's my tangent line at some particular point. What are my units when I find my slope? And again, slope is defined by my rise over run. The rise would be what in units? That would be meters per second, and my run per second. And then we have this fraction divided by a fraction. So because s is always the same as s over 1, right? So what's the rule when we divide by fractions? Here's a tip. Keep, change, flip. And so we have this meters over seconds times 1 over seconds, which would give us meters per second squared, which is what? Acceleration. That gives us acceleration. So this is the important part. This is the important connection. Now, one thing, whenever you see a graph that starts with s of t, then this means the position function. If I take the derivative of my position function, I get what? It would be my velocity. And so v of t refers to our velocity function. This would give us our velocity. And if I take velocity, I take the derivative of velocity, what do I get? Acceleration. So a of t refers to our acceleration. That's some cool math. So we can find if we have a position function, we can find the velocity function just by taking the derivative. Is everybody good? All right. We're going to be talking today about a branch of physics called kinematics. Has anybody heard of kinematics before? Nobody? All right, think of kinematics as the physics of a particle that moves in one-dimensional space. So we're going to evaluate a particle as it moves in 1D space. So if it's one-dimensional, what options does it have as far as movement?
Left and right.
Yeah, that's all it can do is left or right. It can't go up or down. It can't go backward, forward. All it can do is move left or right. Now let's consider, so when we talk about a position function, so that's going to be my, let's see if I can think of let's see if I can think of the best way to do this. S of, let's do it this way. S of t, v of t, and a of t. Now let's look at whether they are positive or negative. And then the meaning. Positive, negative, and then the meaning. Actually, the meaning will be inside. Okay. What do you think it means? What does S of t mean? It's my position. Now, if I'm talking about a graph where I plug in some t value of time and I get a positive value back, what do you think that means as far as position? This means that I am to the right of the origin by that many units. If it's a positive 2, I'm 2 units to the right of the origin. So to the right of the origin. So a negative position would be what? To the left. Okay, what if I have a positive velocity? Any guesses what that means as far as kinematics is concerned? I'm moving to the right. I can be to the left. If this is negative and this is positive, it means I'm on the left, traveling to the right. All this means is traveling to the right. Going or moving to the right. I'll use a different color so we can see the difference. So moving to the right. So a negative velocity would be, yeah, moving to the left. Now, acceleration is a little bit more difficult. And so I really want to compare acceleration to velocity. So I'm going to move down and do another chart for my acceleration. So here is acceleration. I'll do velocity first. Velocity and acceleration. Positive, negative. Oops, let's do this. Let's do it this way. And then meaning. All right, these are all of the possible outcomes. Now let's consider what it means if, so what does it mean if my velocity is positive? I'm moving to the right. What does it mean if my acceleration is positive? I'm accelerating to the right. So if I'm moving to the right and accelerating to the right, what happens to me? I'm accelerating, I'm going faster, right? Speeding up. Okay. What does it mean when my velocity is negative? I'm moving to the left. What does it mean if my acceleration is negative? That actually doesn't mean slowing down. It means that the vector of acceleration is pointed to the left. If my velocity is pointing to the left and my acceleration is pointing to the left, what happens to me? I speed up as well. All right, let's look at the next one. What does a positive velocity mean? I'm moving to the right. What does a negative acceleration mean? My vector of acceleration is pointed to the left. If my velocity is pointed to the right and my acceleration is pointed to the left, what happens to me? I slow down. What if my velocity is pointed to the left and my acceleration is pointed to the right? Yeah, I slow down. So explain to me how you know whether you speed up or slow down. What's a simple way we can wrap our heads around this whole chart here? Yeah, if your velocity and your acceleration are opposite, then you slow down. If your velocity and acceleration are the same, you speed up. Yep, that's sort of how we're going to have to remember that using a chart like that. Any questions so far? Okay, moving on then. Am I going too fast? All right, here's my example. S of t equals 16t cubed minus 36t squared plus 24, where t is seconds and S of t is feet. S of t represents a particle moving in one dimension, in one-dimensional space. What is the initial position? Emerson, any ideas how to figure this out?
Would it just be the, sorry, what exactly is SFT again? I can't really see it very well.
Is it too far back? S of t represents a particle moving in 1D.
Alright, so can you just plug in 0 to find initial direction?
Yeah, that's exactly what you do. So when time is 0, that's the initial conditions. So we substitute t equals 0. So that gives me S of 0 equals 16 times 0 cubed minus 36 times 0 squared plus 24, which gives me what? Just gives me 24. 24 what? What does that mean? 24 what? What are my units? Feet in what direction? Which means what? Yeah, feet to the right of the origin. Oops. It's feet to the right of the origin. That's where I start. So if you wanted to graph this out, here's my Cartesian grid. I start at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I'm way over here. That's my starting location. I'm only moving left to right. Okay. The second question that I have, B, is what is the velocity of the particle at t equals 1? What is the velocity of the particle at t equals 1 second? How do we figure that out? How do I find my velocity? Yeah, we find the derivative and plug in 1. Find the derivative. And plug in t equals 1. Yep, that's exactly what we do. So we need to find the derivative of this. And if we find the derivative, then that becomes our velocity, because the derivative of s of t equals our velocity. What is the derivative of this? Kyle, and it is what the derivative of this is, this position function? Can we just use the power rule? What does the power rule say to do? What is the power rule, Kyle, for this first piece? Don't we multiply our coefficient by the exponent? Okay, does that give us 48? And then what do we do after we multiply the exponent with our coefficient? What do we do with the exponent, Kyle? Don't we subtract 1? So 3 minus 1 would give us 2. Okay, let's do the same thing with this next one, Kyle. What's the first step? By our exponent. That would give us what, 72? So minus 72. T what? To the power of what? Yeah, just 1. Then what happens to this one here, Kyle? It just goes away. Yeah, the derivative of a constant is always going to be 0. The derivative of a constant is always going to be 0. All right, so Eleanor's directions were this: find the derivative, which we did, and then plug in t equals 1. So we'll do that. The next step is plug in t equals 1. So I have 48 times 1 squared minus 32 times 1, which gives me a velocity of what? Negative 24. Negative 24 feet per second, which means what? Yeah, we're moving to the left. So moving to the left. Moving to the left. Yep. What is the speed at t equals 1? What's the speed at t equals 1?
Still be 24 feet per second, but positive.
Yep, because speed is always positive. 24 feet. Yep. If I'm going 24 miles an hour down to St. George, I'm going 24, my speed is 24. If I'm coming back and I'm going 24 miles an hour, I'm still going 24 miles an hour. There's no, speed is not a vector. It does not have direction. Right? What is the acceleration? Part D. What is the acceleration when t equals 1? Riley, how do we figure out acceleration?
We find the derivative of velocity over time.
Yeah, we find the, so here's our velocity right here. And so we're going to find the acceleration. So we're going to, so the derivative of velocity would give us acceleration, which is what?
That would be 96 t minus 72.
Uh-huh. Yeah, so we found the derivative. Did we answer the question?
No, we still have to solve for t.
Okay, if we solve for t, how do we do it?
We find t in the variable there.
Okay, so a of 1 equals 96 times 1 minus 72. Okay, we're getting 24.
Yes.
Again, what are my units? 24 what? Per second squared, yeah. Yep. 24 feet per second squared. All right, so A, B, C, D, we're going to do a question E. E is if the object Is the object speeding up or slowing down? Is the object speeding up or slowing down? Gosh. Slowing down at t equals 1. How do you know?
Because the acceleration is opposite to.
Yeah, because we have the acceleration, which is positive, and we have velocity, which was negative. So we have two vectors. We have one vector of velocity that's pointed to the left. We have another vector of acceleration that is pointed to the right. So that means that you would be slowing down. So the answer is slowing down. Why? Because acceleration, the velocity and acceleration have different signs. There you go. Any questions so far? Okay, part F. When is the particle at rest? When is the particle at rest? How do we find that? Catherine, any ideas? What does it mean that the particle is at rest?
Acceleration is 0.
When the acceleration is at 0. So we need to find what t is when our v of t is 0. So we need to find t when v of t is 0. Well, we have v of t right here. Oh, is that? No, that's not v of t. That's a of t. Where's v of t? There's v of t right here. Okay. So I have 48 t squared minus 32. Was that 30? Was that 72? 72, yeah. 72. That gives me my velocity. Catherine, does that make sense? If a particle is at rest, that our velocity would have to be 0. Okay, so we're going to find when our velocity is 0. Oops. The question is, how do we solve for that? Josh, any ideas? And it turns out we can. In fact, it looks like we could take out even as much as a 24. We could take out a 24 t. What's left over if we take out a 24? Yeah. So t equals what? What? Sorry, what? And 1.5, okay, yeah. And I don't know if it helps. A lot of people like to do these separately. They like to do 24 t equals 0 and solve for that. And then 2t minus 3 equals 0 and solve for that. And you're going to find that here we get the 0 and over here we get the 1.5. So we have t equals 0 and 1.5. My next question is, when is the particle, or what interval is the particle moving to the left? Let's do G. What interval of time is the particle moving to the left? Now, it's important when we're talking about a particle moving to the left and moving to the right, and it's in one-dimensional space. If a particle is moving to the right and it moves in one-dimensional space, what does it have to do before it can move to the left? It has to stop. So according to what our discovery from the previous problem, we only see that the particle stops twice. So, and in fact, usually we don't consider time before time 0 anyway. But let's just say that we're going to use what's called a sign diagram to determine what intervals the graph is moving to the left and to the right. So we are going to use we're going to use a sign diagram to determine where or when the particle is moving to the left or right. So here's our, so we draw a line, and then we're going to indicate the 2 points where the graph stops. At what times the particle stops? At what times does the particle stop? T equals what? 0 and 1.5. Okay. Now our equation for the velocity, and that's the whole point, we're trying to figure out where the graph moves, where the particle moves left and right. We are going to use the velocity equation because that's going to tell us the position equation doesn't tell us whether we're moving left or right. The position function tells us what? Where we are, whether we're to the left or to the right. It doesn't tell us whether we're moving left or right. It tells us whether we are on the left-hand side or the right-hand side of the origin. So I want to use our velocity equation. And what was that velocity equation in factored form? V of t equals what? 24. T equals 2t minus 3. So because we call this a sign diagram, all I care about is the sign. Just tell me whether it's positive or negative. Now give me a number over here that could be representative of this interval. -1. If I plug -1 into here, is this positive or negative? I get negative. And if I plug negative, so I'm going to use, let's use t equals -1. And so if I plug in -1 here, this becomes negative. If I plug -1 in here, is that positive or negative? Yeah, this is going to give me a negative value minus another value is a negative. So I have a negative times a negative, which is a what? So is the particle for this interval here from -infinity to 0, is the particle moving left or right? It's moving right. How do you know it's moving right? It's a positive velocity. Because it's a positive velocity, it's moving to the right. Give me a number that would be representative of this interval. Yeah, let's use t equals 1. If I plug t equals 1 in here, all I care about is the sign. Do I get a positive or negative value? If I plug 1 here, okay, that's going to be positive. And if I plug in 1 here, louder, it's going to be negative. And a positive times a negative? What does that say about the particle between these two intervals, or between 0 and 1.5? It's going to be what? It's moving left. Yep, the particle is moving left for this entire interval. From 0 seconds to 1.5 seconds, it's moving left. All right, what's a number over here that would be representative of this interval? What's a number? 2. Okay, let's use, could you use 5 or 10 or 100? We could use anything over here. So yeah, let's use 2. Okay, if I plug in 2 over here, is that positive or negative? Okay, that's positive. If I plug in 2 over here, positive. What's a positive times a positive? So what does that say about the particle over here after 1.5 seconds? It's moving to the right. Yep, good. So did we answer our question? What does it say? It says, what interval of time is the particle moving to the left? Yeah, it's from 0 to 1.5. Now this might shock you because some of you might think, well, you're not really moving at all at 0, and you're not really moving at all at 1.5. So we should use parentheses because those endpoints are not included. But that's actually not true. We're going to use brackets, and I think it's more of the way we speak. When we talk about an interval, what we don't say we go from left, we're moving left from 0, infinitely close to 0, to 1.5, infinitely close to 1.5, not included. When we talk about when we're moving left, don't you just say we move left from 0 to 1.5? Isn't that how we just talk? We don't say we're infinitely close. We just say we're traveling from 0, we're going left from 0 to 1.5. And because the way we talk, we travel from 0 to 1.5, we're going to use brackets saying it's included. Now I get it. I get the argument that we're really not moving any direction at that instantaneous moment. But nevertheless, we're going to say that those endpoints are included. So this is our answer. That is the answer right there. Okay, moving on. H. Is anything confusing that we've talked about so far, or is it more about just wrapping our heads around the ideas? H. When is the velocity of the particle equal to 54 feet per second? When is the velocity of the particle equal to 54 feet per second? Is everybody caught up? Is that too small? Probably. Huh? How do we do that? When is the velocity of the particle equal to 54 feet per second? How do we figure that out? Okay, so our velocity equation is what? It was, that's right there. It is V of t equals 24t times 2t minus 3. Where do I plug this 54? Yeah, for V of t. That is my new velocity. So I'm going to plug it in right there. I have 54 equals 24t times 2t minus 3. I actually think it'd be easier to use our other equation before we factored. Otherwise, we have to think of what's a t value that gives me 54 over here. That's going to be very difficult to try to figure out. It's easier if it's 0 over here. So let's just distribute that back. So I have 54 equals 48t minus 72. So what, 72t? 48t squared. Thank you. Is that the equation? Okay. Now what? Yeah, we can subtract 54 from both sides and we have a quadratic. We have 0 equals 48t squared minus 72t minus 54. How do we solve for this? Can we factor? I know a 2 could come out. What else can be factored out of this? What can be factored out of it? Can we factor out of 4? Can we factor out of 6? 7, 8, 9, 8, 9, 10, yeah, looks like we can factor out of 6. So if we factor out of 6, how do you know we can factor out of 6 by looking at that? Well, one thing we can tell is that they're both even, right? All of these are even, so I know that they're divisible by 2, but how do I know they're divisible by 3? Yeah, we add up both of the digits, and here I get 4 plus 8, which gives me 12. 3 goes into 12, so 3 goes into this. 7 plus 2, 7, 8, 9, that gives me 9. 3 goes into 9, so 3 goes into that, and there's 9 as well here if I add up the digits. Yep. So I know if all 3 of these terms are divisible by 2 and 3, then they're all divisible by 6. So I'm going to factor out a 6. So that gives me 6 times what? AT squared minus 12t minus 9. Should we try to factor it? I don't know if it's factorable, but we can try. Work. Close. Yeah, I think that's always, if you spend a lot of time, it might not even be factorable. So we're spending a lot of time for something that might not even pay off. But the quadratic formula always works. The quadratic formula always works. So we should use this. What is the quadratic formula? Nice. Who said that? Chris, good job, Chris. What are my ABC values? Yep. So let's plug those in and see what we get. Could we have used these instead? This is A, this is B, this is C. Yeah, we'd get the same answer. So this gives us X equals negative B, which is negative 12, plus or minus the square root of B, which is negative 12. Make sure you have a placeholder for this, or you're going to get the wrong answer. Minus 4AC all over 2A. Okay, so that gives us negative is a positive, 12 plus or minus the square root of 144. Negative and a negative are a positive, so that's going to be a plus something. Plus 288. Does that sound right? Yes, no, maybe so. Yeah. All over 16. 12 plus or minus the square root of 432. So I'm getting, it wasn't really X, it was T, right? I'm getting that our time is 2.049 seconds and negative 0.549 seconds. What do these mean? What's happening in 2.049 seconds? Yeah, that's when the particle's speed is 54 feet per second. That was the whole point. We're trying to find when the velocity was 54, and we just found it down here. Those are our answers. Now, normally this doesn't count. Usually the problem will say for t values, it'll say in the problem for t values that are 0 or greater. Because what does that mean, a 0 time? 0 time is before we start keeping track. So, questions? Good. What's the difference between distance and displacement? Yeah. So when we talk about a displacement, we are talking about the distance between you and the origin. We're just talking about that, the distance you are away from any particular, whatever your starting point is. So the displacement is the distance from a particle to the origin. What's the displacement? St. George is almost exactly a little bit more than 300 miles south of Salt Lake City. Not as the, what did they say, as the crow flies? No, it'd be actually the drivable distance. So if I drive down to St. George and I go, so let's say that it's 300 miles away, and then I turn around and I come back to Salt Lake, what is my displacement from Salt Lake? It's 0. Yeah, your measurable distance from Salt Lake at that particular point is 0. What is your distance traveled? Yeah, it would be the 300 miles down there and 300 miles back, so about 600 miles. So does your odometer in your car, does it measure displacement or distance? Distance, yep. So displacement is the distance from a particle to the origin, and the distance is the actual distance traveled. Distance is the amount traveled, the total amount traveled. How about that? The total, trying to avoid using distance, right? When you define something, it's sort of weird when you use the same word in the definition. It's like a school. What is a school? A school is it's a building that's a school. No, that doesn't make sense. You need to try to avoid that word. So the distance is the total amount, I wrote that, total amount traveled. How do you feel about the difference between the two? Okay, so I want to know the displacement of the particle. So we're using the same equation. This is I want to know what is the displacement of the particle between t equals 0 and t equals 2 seconds. How do we do that? How do we find the displacement? What equation do we use? Do we use position, velocity, or acceleration? We use position. In fact, if the only thing that matters is that the difference between now and where we started, then we could use our position function and plug in t equals 2 minus using the position function and substituting in t equals 0. So I'm going to use our equation of, so use our s of t function, our position function of 16t cubed minus 36t squared plus 24. And we're going to substitute in 2. So I have 16 times 2 cubed minus 36 times 2 squared plus 24 minus the same equation, 16 times 0 cubed minus 36 times 0 squared plus 24. Does that make sense that that's how we're going to set it up to find the displacement from 0 to 2 seconds? If it doesn't make sense, that's something we need to talk about. Does this make logical sense that that's how we could find the displacement? Okay, what do we get? What does this part here become? what does this part here become? Nobody has it? It is 8. Yep, it's 8. Minus what? What's all this? Yeah, it's 24. So what's my answer? Negative 16. Negative 16. What does that mean? Negative 16 what? Oh, this is, it's a distance, right? Not a velocity, since we used our position. From where? Is it from the origin? Yeah, we're from our starting position, right? It's 16 units or 16 feet in what direction of our starting position? 16 feet what? It's 16 feet to the left of our starting position. What this means is 16 feet to the left of our, that's not wrong, our starting position. Correct. All right, the next question is, what's the total distance traveled? Is it the same? Can the total distance traveled be less? No, it can't be less. Can it be more? How? How can it be more? Yeah, I could go, if this is, so we start it, we're starting at 24, and I could, and here's 8, and I could, I'm going to the left, I pass it, and then I come back. So my displacement is still this distance here, but my distance traveled is a little bit more. The question is, how do we find that little bit more? Add what? So let's talk about this again. So we're starting at 24. In fact, let me write down the question first. I want to know the total distance traveled. So I'm going to go to the top. Then I have J. What is the total distance traveled from t equals 0 to t equals 2. Now let's try to wrap our heads around what's happening here. Now so if the distance traveled cannot be less than the displacement, but it is possible for the distance to be more. If we're starting at 24 and we're moving left 16 units to 8, that's our displacement. If the distance is bigger than the displacement, then the particle passed 8. I'm going to actually write it down further. It passed 8 and circled around and came back. Now, because this particle is moving in one dimension, in one-dimensional space, what has to happen here? It has to stop there. So this is t equals 2. Sorry, 0. This is t equals 2. What is this? T equals what? This is t equals 0. Yeah, didn't we already figure out where we stopped? Where did we stop? Yeah, we stopped here at 0 and 1.5. So we already have that information. We can plug that in. So we know that the particle stopped at 1.5. Does that make sense how we figure out this extra piece here? If it doesn't make sense, we need to talk about it. If the particle doesn't stop, then the displacement and the distance are the same. If the particle doesn't stop and reverse directions, then the distance and the displacement are the same. Because it does stop, I need to figure out what the discrepancy here is. How do I find out what this extra distance here is? How do I find out this extra piece? All I have to do is find it once, right? If I can find this distance here, then multiply it by 2 and it gives me the other piece here. Yeah, find the position. Find the position when t equals 1.5. Yep. Find the position when t equals 1.5. That means we have to use the position equation. We have to use s of t equals 16t cubed minus 36t squared plus 24. Anybody have a calculator? We plug that in. What do we get? You got -3. So this is -3 right here. That's our position. Right? Our position is -3 here at when t is 1.5. So how much more did it travel? How much? What's this distance here? $11. We just find, yeah, just the difference between those points is your distance. So, you know, -3 minus 8 would give us, well, -11, but they also value because distance is always positive. And so I get 11 here. And then what about this distance here? 11. So how much more than the displacement did we travel? 22 units. We traveled 22 more units. So our displacement, so we traveled 22 more units plus the displacement. So that's 22 plus what? What's the displacement? What was the displacement? 6, yeah. We don't need to have it positive because distance is not a vector. Distance is not a vector, it's just a quantity. So how much is it? What's our distance traveled? Yeah, 38 units, 38 feet. Yeah. Yeah, that's it. 38 feet. Our displacement was negative 16, sorry, 16 units to the left of our origin. How much did we travel? Well, we traveled 38 feet total. Are you confused? I think doing your homework, I think that's going to give you more guidance. It'll give you a repetition on the same concepts. All right, here's another piece of, this is another idea. Are you guys still copying? Catherine, how are you doing? Okay, let's look at another one. This is my S of t, which means what? Yeah, this is just my position. Let's do that one a little lower. There's a point that's almost right in here. What's that called? Starts with an I. Yeah. What does an inflection point mean? When it changes concavity. What kind of concavity do we have here? What's that? Concave up. What about here? Concave down. Good. That was just a sidebar. All right, here's my question. So this is going to represent, this graph represents a car. And I want to know, is the car going faster at Is the car going faster at A or C? Is the car, if this represents the car, is the car going faster at A or C?
You're right, since the slope is a lot steeper there and that's
When we talk about this is our position function, and the velocity of a position function is our slope. Our slope here is a lot steeper. In fact, that almost looks like, well, you could say it's maybe here, but A is a lot steeper. And so the answer is A. A, because the slope is steeper. Okay, a lot of this you just have to do, just get exposed to it a lot before you start feeling more comfortable with it. Is that too small? I want to just be able to see the graph. If it's too small, I have to zoom in. I'll just have to figure it out. B. When is the car stopped? Or is the car stopped? Do I have a stopped car? When is the car stopped? Yeah, it looks like it stopped here, C and D. The car is stopped. Between C and D. How do you describe why it is stopped here? It has a slope of 0, so my velocity is 0. Another way of wrapping your head around it is that if this is distance, if this is our distance equation, then the distance traveled is not increasing or decreasing from C or D, which implies that the car has stopped. All right, what about, here's my next question. I want to know at what point is the car's velocity the greatest? I'll give you a hint. It's a trick question. At what point is the velocity the greatest? And you might be saying, why are you giving us a trick question? Because you could have a question like this on your AP test. The velocity, the greatest. Giving you a hint, it's a trick question. When is the velocity the greatest?
Well, seemingly it's D through E, but would,
So Riley says that it would say it's over here somewhere, but it's a trick question. Why is the answer not E? E is negative. What's greater, a positive or a negative number? A positive number. So where do we have the greatest velocity? Maybe A or B, yeah. So from A to B, or in this area here, looks like we have the greatest. From A to B is the greatest velocity. From A to B, we have the greatest velocity. And then the last question is, where do we have the greatest speed? That is E, because speed is always positive. So it doesn't matter that my slope is negative here. We still just calculate the number that represents that slope. What's my rise over run, ignoring the negative? So E is the answer if we're talking about speed. If we're talking about velocity. One more time, why is E not the greatest velocity? Because it's negative. So at what point is the speed the greatest? And the answer in this case is E. Let's zoom out so you can see everything. What was the most confusing part of today? Distance versus displacement? What equation to use? Velocity, acceleration, or position? Josh, any thoughts?
Maybe like the displacement or the distance, but like, especially like that part where it goes past, stops, and comes back.
Yep. Because you have to try to figure out that distance, right? I agree that seems so. In calculus, displacement is fairly easy. Once you learn the integral, displacement is going to be a piece of cake. But the problem is when they ask you what the distance traveled is. How did we find that extra piece? We have to take into account what? We have to find where it stops, because where it stops, that difference between where it ends up and where it stops and comes back, we have to add that extra distance to the displacement. I agree, that is a confusing part. That's just something we have to wrap our heads around by doing more problems like that. Let's go all the way back to the beginning. Are you okay? This is a super important idea. I hope that we feel comfortable with that. That the slope of the distance versus time is what? It's velocity. If you have velocity versus time, then the slope is what? Acceleration. How do you find a slope equation? How do you find a slope equation? If I give you if I give you some equation, how do you find a slope equation? You find the derivative. That's the point of a derivative. The point of a derivative is to tell you the slope at any given point. Are we going to be doing this the entire year? Yes, we're going to be doing derivatives the entire year, all the way through May and June. Actually, after the test, I'm going to have you guys do a presentation on whatever topic that we've talked about. I want you to reteach it. That's going to be the last project after we're done with the AP test. Any project, anything, if you like kinematics, you can do your presentation on kinematics. What about this part? Was this confusing? About it? Okay, let's talk about this again. If your S of t is positive, what does that mean? You're to the right. Your position is to the right of the origin. What if it's negative? Your position is to the left of the origin. What if your V of t is positive? You're moving to the right. Could you be to the left? Can you be on the left but moving to the right? Yeah, you could. What about your V of t if your V of t is negative? You're moving to the left. How do we know whether we are accelerating? What have to be the same signs? Velocity and acceleration, if they're the same signs, either both positive or both negative, then you are speeding up. How do you know if you're slowing down? If your velocity and acceleration are different signs, if one's positive and one's negative, then you are slowing down. Those are important ideas. One more time, how did we find our velocity equation? Just take the derivative. Do you remember the power rule? We need to review the power rule because some of you, Kyle, some of you don't remember the power rule. If I have y equals a times x to the power of n, that is my, let's say that this is my position function. How do I find the derivative or my velocity function? A times n. Nice, cool. That is called the power rule. You will also need to remember, your product rule. What is the product rule? If I have y equals f of x times g of x, two functions that we're multiplying together, then the product rule is what? Correct. F of x times the derivative of g of x plus g of x times the derivative of f of x. What about the quotient rule? Quotient, this is the last one. Quotient rule. If I have, okay, I have my function of f of x over g of x. The derivative is going to be what? Low d high, high d low, over low low. Good job. Low d high minus high d low over low low.